Welcome to the video on Colpitt's oscillator. What is meant by Colpitt's oscillator? An LC oscillator which uses two capacitive reactances and one inductive reactance in the feedback network, that is in the tank circuit, is called as Colpitt's oscillator. So this is the circuit diagram of Colpitt's oscillator, and this circuit is exactly same as Hartley oscillator except one change. Okay, so the change is here in the tank circuit we are using two capacitors and one inductance. It is called as Colpitt oscillator, and in the tank circuit of the Hartley oscillator we can use two inductor and one capacitor. So the circuit is same as Hartley oscillator except that the inductors and capacitors have exchanges places in the tank circuit. The amplifier stage uses an active device as a transistor in the common emitter configuration, which is shown in the figure. And in this circuit diagram, the tapped coil in the Hartley circuit, the tapped capacitor produces the required phase shift. That is, this tapped circuit, the tapped capacitor, which produces 180-degree phase shift for the feedback. So almost the circuit is same as Hartley oscillator except the tank circuit, and this common emitter amplifier produces 180-degree phase shift and this tank circuit produces 180-degree phase shift. So the total phase shift can be given as 360 degree to satisfy the oscillating conditions. And this is the equivalent circuit of Colpitt's oscillator. So you are seeing the circuit here. From this circuit we can see the capacitor C1 is parallel with HIE and C2 is across RL. So the inductance L3 is connected between the input and output. Yes, now you can see the derivation of frequency of oscillations. So the general equation for LC oscillator can be given as HFE Z1 into Z2 plus Z3 Z1 plus Z1 Z2 plus HIE Z1 plus Z2 plus Z3 equal to 0. So this is the master equation for LC oscillator. So to determine the frequency of oscillation, the imaginary part must be equal to 0. So before that we must substitute the value of Z1 and Z2 and Z3 in this equation. So let the value of Z1 is equal to minus j by omega C1, Z2 is equal to minus j by omega C2 and Z3 equal to j into omega L. So now we can substitute these three values in this master equation, and yes, after substituting the values we can get this equation minus HFE by omega square C1 C2 plus L by C1 minus 1 by omega square C1 C2 plus HIE into minus j of omega C1 minus j of omega C2 plus j omega L equal to 0. So after this equation we can get this equation. So here I'm going to take this j as common. So after taking j, I can get the equation as plus JHIE into minus 1 by omega C1 and minus 1 by omega C2 plus j omega L equal to 0. The remaining all are same. So in this equation, this third term is the imaginary term and this first three terms are called as real term. So to find the frequency of oscillation, we must equate the imaginary part equal to 0. So this term equal to 0. So HIE into minus j of j by omega C1 minus j by omega C2 plus j omega L equal to 0. So I am going to take HI in this denominator. So 0 by j HIE is equal to 0. So minus 1 by omega C1 minus 1 by omega C2 plus omega L equal to 0. So omega L equal to 1 by omega C1 plus 1 by omega C2. So I am going to take this omega as common and this omega is going to this side. So I can get omega square L equal to 1 by C1 plus 1 by C2. So finally omega square equal to 1 by L C equivalent. So CEQ is nothing but as equivalent capacitance. Okay. So where C equivalent can be given as C1 C2 by C1 plus C2. Okay, it can be rewritten as 1 by C1 plus 1 by C2. Now you can take C2 C1 by C1 plus C2. Now omega equal to, So omega square equal to 1 by L into C equivalent. Now what is omega? Omega equal to 1 by root of L C equivalent. So omega is nothing but a frequency of oscillation. So omega equal to 2 pi f. So 2 pi f equal to this term, and then f equal to 1 by 2 pi root of L C equivalent. So where Ceq is called as equivalent capacitance. So this is the final equation for frequency of oscillations of Colpitts oscillator. Now we can find out the real part. So now you can equate the real part equal to 0. So in this equation, this first term, second term and third term are called as real terms. Now, yeah, minus HFE by omega square C1 into C2 plus L by C1 plus minus 1 by omega square C1 into C2 equal to 0. Okay, so now you can simplify this equation. So after simplifying the equation, we can get as 1 by omega square C2 into HFE plus 1 equal to L. So again 1 by C2 equal to HFE plus 1 equal to omega square L. I am going to take this omega square into this right hand side. So this omega square L equal to can be also written as 1 by C1 plus 1 by C2, because we already found out, yeah, here omega square L equal to 1 by C1 plus 1 by C2. Now I can substitute this equation as in this equation. Okay, so now 1 by C2 into HFE plus 1 equal to C1 plus C2 by C1 into C2. That is what equivalent capacitance. Now HFE1 plus HFE plus 1 equal to C1 plus C2 by C1. So in this term I can find out the value HFE equal to C2 by C1, capacitance 2 by capacitance 1. So the HFE can be called as hybrid forward gain is equal to C2 by C1. So the final equation, so what we have to understand is this F equation is very important for frequency of oscillations. For Hartley oscillator, F equal to 1 by 2 pi into root of C into L equivalent. Okay, that is what equivalent inductance. LEQ equal to L1 plus L2. Here C equivalent CEQ equal to 1 by C1 plus 1 by C2. Now you can see the advantages of Colpitts oscillator. What are the advantages? So by using the Colpitts oscillator, the performance remains very good even at the higher frequencies, and it has the capacity to produce more pure waves, and the final one is it has wide range of frequencies. So these are the possible advantages, and the drawbacks are it is very hard to construct the design, and whenever the capacitor value can be changed, it becomes more difficult to adjust the feedback. Because of the circuit bulkiness, the cost also increases. Thank you.